Okay, so in this next problem we are asked to determine whether each point lies on the graph of the equation, and the equation we're given is y equals the square root of x plus 4, and I put the whole thing in parentheses to indicate that the square root is going over x and the plus 4. And the points we're given are 0, 2 and 5, 3. Now, there are multiple ways you could do this. There are multiple ways you could do this. One way would be to graph this equation and see if these points lie on that graph, but that might take some time, and with more complicated functions it would become inefficient and inconvenient. Alternatively, another, I think, simpler way of doing this is to just plug in these points to this equation, and if the left side equals the right side, then you know that yes, this point does lie on the graph of the equation. So for example, with this first set of points, 0, 2, we plug in 2 for the y value, and we say equals the square root of 0 plus 4. Well, the square root of 0 plus 4 is just the square root of 4, and the square root of 4 is just 2. So we know that this does lie. This does lie on the graph of the equation. So then we check this one, 5, 3. We plug in 3 for y, and we do the square root of 5 plus 4. Well, the square root of 5 plus 4 is the same thing as the square root of 9. And the square root of 9 is just 3. So both of these points do indeed lie on the graph of the equation. Okay, so in this next problem we're given the exact same directions, determine whether each point lies on the graph of the equation, but we're given a different equation and different points. This time our equation is y equals x squared minus 3x plus 2, and our points are 2, 0 and negative 2, 8. So now that you saw the last one, I want you to pause the video and we'll come back to it and see how you did. So, assuming you pause the video, let's walk through this and see how it would have been done. So for this first point, 2, 0, we plug in 0 for the y, and we plug in 2 for the x. So every time we see x, we're just going to replace it with 2. So that gives us 2 squared minus 3 times 2 plus 2. Now, 2 squared is 4, and negative 3 times 2 is negative 6, and that's going to be plus 2, and then 4 minus 6 is negative 2, so we're left with negative 2 plus 2, which is 0. So we can say that 0 equals 0, and this point 2, 0 does lie on the graph. Now we get to negative 2, 8. So we plug in 8 for y, and negative 2 every time we see x. So negative 2 squared minus 3 times negative 2, and then plus 2. Negative 2 squared is 4. Negative 3 times negative 2 is 6. And then we have plus 2. Well, 4 plus 6 is 10, and 10 plus 2 is 12. So we have 8 equals 12, which is not true. So this point does not lie on the graph of this equation. Alrighty, so in this next problem we are given the exact same directions, determine whether each point lies on the graph of the equation, but once again we're given a different equation and different points. This time our equation is y equals the absolute value of x minus 1 plus 2, and our points are 2, 3 and negative 1, 0. So the first thing you're going to want to realize is that when you have an absolute value, anything that's in between these two absolute value signs, it means when you evaluate it using the absolute value, it will be positive. So the absolute value of -7, for example, is just 7. The absolute value of 1 is just 1. And the absolute value of 0 is just 0. So knowing that, let's solve this and see if any of these points satisfy this equation. So for the first point, we'll plug in 3 for y, and we'll plug in 2 wherever we see x, and then we will add that plus 2. And in terms of order of operations, the absolute value sign works similar to parentheses. So you want to solve whatever is in the parentheses before, or you want to solve whatever is in the absolute value before continuing on to this plus 2. So 2 minus 1 is just the absolute value of 1 plus 2. And the absolute value of 1 is just 1. So then we're left with 1 plus 2. And then 1 plus 2 is 3. 3 equals 3. So 2 comma 3 does lie on the graph of this equation. Now we have -1 comma 0. So we're going to plug in 0 for y, and -1 wherever we see x. So -1 minus 1 plus 2. So that's going to give us -1 minus 1 is -2. And don't fall for the common mistake where you add the -2 to the 2 and say it's 0, and this does lie in the graph of the equation, because remember, it's between the absolute value sign, and anything that's between the absolute value sign, it will become the positive number of that number, if that makes any sense. So -2 will become just 2, and we have 2 plus 2. And we can see here that 0 does not equal 2 plus 2. So -1 comma 0 does not lie on the graph of this equation. So in this problem, we are given the exact same instructions to determine whether each point lies on the graph of the equation, but this time we're given a different equation and once again different points. Our equation this time is x squared plus y squared equals 20, and our points are 3, comma -2 and -4, comma 2. So in order to solve this, we would just plug in the x and the y values on this point into the x and the y values in this equation. So our x value here is 3, so we would do 3 squared, and then our y value is -2, so we would do plus, and then in parentheses, -2 squared. And it's very important that you do this, because saying 3 squared minus 2 squared would mean something different, and we'll see what that means after we solve this. And then we set that equal to 20. So 3 squared is 9, and -2 squared is 4, and that's going to equal, and we're going to set that equal to 20. But if we look, 9 plus 4 is 13, and 13 is not 20. So 3 comma -2 does not lie on the graph of this equation. For this next one, we'll plug in -4 for x, and again we're going to put it in parentheses. -4 squared plus 2 squared equals 20. -4 squared is 16, and 2 squared is 4, so we have 16 plus 4, and we're going to set that equal to 20. Well, 16 plus 4 is 20, so we know that the point -4 comma 2 does lie on the graph of the equation x squared plus y squared equals 20. Now, back to here, what would happen if we didn't use this parentheses? Well, we'd have 3 squared minus 2 squared equals 20. Let me write that better. So 3 squared is 9, and then we would have it minus, but because there's no parentheses, we wouldn't know that this minus is going to the 2. So we would just write 9 minus 4 equals 20, and we'd get 5 equals 20. So regardless, we would still end up saying that this point doesn't lie on the graph of that equation, But in this scenario, we would be saying that for the wrong reason. Our math is wrong in this second scenario here. Okay, so in this next question, we are asked to complete the table below and use the resulting points of use the resulting solution points to sketch the graph of the equation. And the equation we're given is y equals negative 2x plus 5. Now, just from this graph, you could graph this graph without having any of these points, but because it asks us to fill in the table, we're going to write that down. So basically we're given the x values and then we're asked to find the y value and write that in the ordered pair form. So in order to do that, we're going to take this equation and plug in whichever one of these x values you want whenever we see the letter x, or the variable x. So for example, with this first one, negative 1, we're going to plug in negative 1 wherever we see x. So we have 2 times negative 1 plus 5. And negative 2 times negative 1 is 2, because a negative times a negative is positive. And we get 2 plus 5, and we get y equals 7. So then our first point that we would end up graphing on the graph is negative 1, 7. So then for this next one, for 0, we're going to plug in 0 every time we see x. So that's going to give us negative 2 times 0 plus 5. Well, negative 2 times 0 is just 0, so we're left with y equals 5. Meaning that our ordered pair will be 0, 5. Then for 1, we're going to plug in 1 wherever we see x. So we have negative 2 times 1. And that's going to be plus 5. Well, negative 2 times 1 is just negative 2. And negative 2 plus 5 is just 3. So then our ordered pair is going to be 1, 3. And then for the point 2, or the x value 2, we're just going to do the exact same thing. Y equals negative 2 times 2 plus 5. So negative 2 times 2 is negative 4. And that's going to be plus 5. And negative 4 plus 5 is just 1. So our ordered pair is going to be 2, 1. And then our last point is 5 over 2. So we have y equals negative 2 times 5 over 2. And that's going to be plus 5. We can cross-reduce this 2 right here, so that's going to give us negative 5 plus 5. And that's just going to be y equals 0. Oh, sorry. So now when we go to graph this, we go over here to this graph and we say, okay, our first point is negative 1, 7. Well, here's negative 1, we're going to the left of the origin by 1, and we're going up 7, which is going to be somewhere off this graph, probably around here, I'd say. Then our next point is 0, 5. So we go at the origin and then up 5. So right around there. And then our next point is 1, 3. So we go to the right of the origin by 1 and up 3. And then our next point is 2, 1. So we go to the right of the origin 2 and over 1. And then our next one is 5 over 2, which is just 2.5 and 0. So we go to the right of the origin 2.5, and then that's just going to be our point right there. So if we were to sketch the graph, it would look straighter than that, but it would look something like this. That's a very rough sketch, and you'd probably want to do a better job on a test or a quiz, but yeah, that's how you do that one. Alright, so in this next question, we are given the exact same instructions, just a different equation. This time the equation is y equals x squared minus 3x, and instead of 5 over 2 for this x value over here, we're just given 3. So now that you saw how to do the last one, I want you to pause the video for this one, try it, and then unpause it, and we'll see how you did. So assuming you try the problem, let's see how it would be done. So once again, like last time, we're going to take each of these x points and plug it into wherever we see x, and that's going to be our y value at that x value on the graph of this equation. That's basically the theory behind these problems. So for -1, we're going to do y equals -1 squared, and again we want to put the whole -1 in parentheses because it changes the meaning if you don't remove the parentheses, and then minus 3, or it changes the meaning if you do remove the parentheses, I'm sorry. -3 times -1, so -1 squared is just 1, and -3 times the -1 is going to be positive 3, so we get y equals 4. So that's -1, 4. And then for 0, we're going to do the same thing. Y equals 0 squared minus 3 times 0. Well, 0 squared is just 0. And 3 times 0 is 0, and 0 minus 0 is still 0, so y equals 0. So our ordered pair is going to be 0, 0 for that one. And then for this one, y equals, or x, for the x value of 1, we do y equals 1 squared minus 3 times 1. So 1 squared is just 1, and -3 times 1 is -3. So y equals -2. So our ordered pair is going to be 1, -2. So then for this one, for the x value of 2, we do the exact same thing. Y equals 2 squared minus 3 times 2. So 2 squared is 4. So y equals 4 minus 3 squared is 6, which would give us y equals -2. So our ordered pair is going to be 2, -2. So then for 3 here, for the very last x value, y equals 3 squared minus 3 times 3. Well, 3 squared is 9. And 3 times 3 is 9. So y equals 0. So then we have the point 3 comma 0. And again, you don't have to do this table ordinarily. You could just graph this by plugging in whatever x value you wanted and just seeing what it is. This is going to be some sort of upwards facing parabola. But for the purpose of this problem, they do want you to fill out the table, so that's what we're doing. So this first point is -1, 4. So we go to the left of the origin by 1, and then we go up 4 to this point right here. And then our next point is 0, 0. So we go to the exact center, the origin. We make a circle there. And our next point is 1, -2. So we go to the right 1 and down 2. And then the next one is 2, -2. So we go to the right of the origin by 2 and down 2. And then the next point is 3, 0. So we go to the right of the origin by 3, and then we just make our graph there on the axis. So if we were sketching the graph, I would sketch something like this. And as you can see, this is an upwards facing parabola. Okay, so in this next question, we're asked to graphically estimate the x and y intercepts of the graph, and then verify our results algebraically, meaning take our results that we estimated graphically and plug it into the equation to see if it works. So if you don't know what an x or a y-intercept is, the x-intercept is the point where the point is directly on the x-axis, meaning the y value is going to be 0 on the x-intercept. And it's a similar thing with the y-intercept. The y-intercept is the point where it lies directly on the y-axis, which is where the x value would be 0. So a y-intercept is always going to be 0, comma, some number y, and the x-intercept is always going to be, is this going to draw it? Oh, it's always going to be some number x, comma, 0. So knowing that, they want us to look at the graph and just kind of make an estimate of where the x and the y-intercepts are, and then verify our results algebraically. So for this x-intercept, I can see that this is going by 2, and the point that comes into contact directly with the x-axis looks to be in between 2 and 4, which would be 3. So I'm going to say the x-intercept lies on 3, 0. And then for this y-intercept, you can see at the point 8, the line is just barely to the right of the y-axis, and at the point 10, the line is just barely to the left of the y-axis. So I'm going to say it's in between those, and I'm going to say that the y-intercept is 0, 9. Now, that means that if we plug in 3 when we're verifying our results algebraically, when we plug in 3 for x, we should get 0, or alternatively, when we plug in 0 for y, we should get 3 for x. And when we're verifying our y-intercept algebraically, if we plug in 0 for x, we should get 9 for y, or if we plug in 9 for y, we should get 0 for x. So let's verify our results algebraically. Let's start with the x-intercept. I'm going to plug in 3 for the x value and 0 for the y value, and we'll see if the equation is satisfied. So 0 equals 3 minus 3 squared. Well, 3 minus 3 is 0, and we're doing 3 minus 3 because of the order of operations. So we have 0 squared. 0 squared is 0, so 0 equals 0. So that is satisfied. This means that it is the x-intercept. Now for the y-intercept, I'm going to plug in 9 for y, and 0 for x. So we have 9 equals 0 minus 3 squared. Well, 0 minus 3 is just negative 3. And negative 3 squared is 9. So we get 9 equals 9, which is true, which means yes, this is the y-intercept and this is the x-intercept. Okay, so in this next question we're given the exact same instructions to graphically estimate the x and the y-intercepts of the graph and then verify our results algebraically. This time though we're given a different graph. We're given the graph of an absolute value equation, and the equation we're given is y equals the absolute value of x plus 2. So now that you've seen how to do the last one, I want you to pause the video here and try this one for yourself, and then we'll come back and see how you did. So assuming that you've paused the video and tried it for yourself and unpaused the video, let's see how this would be solved. So if we're graphically estimating the x and the y-intercepts, we want to look for the point on the graph that is on the x-axis and on the y-axis. And on the x-axis we see that the point lying directly on the x-axis looks to be negative 2, 0. And the point lying directly on the y-axis seems to be 0, 2. So now in order to verify our results algebraically, we plug in this x value wherever we see x, and we plug in this y value wherever we see y, and the two things on the left and the right side of the equal sign should be equal to each other. That would verify the results. If they were not equal, then we know we've done something wrong and that the points that we picked were not the x or y intercept. So for this first one, I'm going to plug in negative 2 for x and 0 for y. So 0 equals the absolute value of negative 2 plus 2. Well, negative 2 plus 2 is just 0, and the absolute value of 0 is 0. So 0 does indeed equal 0, meaning that these coordinates do satisfy this equation and that it is the x-intercept. Now we do the same thing for 0, 2. I'm going to plug in 2 for y and 0 for x. So we have 2 equals the absolute value of 0 plus 2. Well, 0 plus 2 is just 2, and the absolute value of 2 is still 2. So we have 2 equals 2, which is a true statement, which means that this is the y-intercept. Okay, so for this next problem, we are asked to find the x and the y-intercepts of the graph of the equation. And the equation we're given is y equals 5x minus 6. Well, recall that for the x-intercept, the number is always going to be x, 0. So for the x-intercept, the y value is always going to be 0, and the x value is going to change depending on which equation we're given. And for the y-intercept, it's always going to be 0, y, meaning the x value, the x value is always going to be 0, and y is going to change depending on which equation we're given. Which means that we know, depending on which one of these intercepts we're finding, one of the variables in this equation is going to be 0. So let's start by finding the x-intercept, and I'll just abbreviate it to int. So for the x-intercept, we know that the y value is always going to be 0, so we can plug in 0 for y, and we get 5x minus 6. Now here we have an algebraic equation with just one variable, so we can just solve for x. So the first thing we're going to do is we're going to try to get x by itself by adding 6 to both sides. So now we have 6 equals 5x. And the reason we're doing this is that because when we solve for x, we are finding what the x value is when the y value is 0, which is our x-intercept. So finally, to get x alone, we're going to divide by 5, to get rid of the 5x here to get x alone, and we get that x equals 6/5, meaning that our x-intercept is 6/5, comma 0. Similarly, for our y-intercept, we're going to do the same thing, except we're going to change which variable is going to be 0. Now, instead of the y being 0, we're going to plug in 0 for x, because that's how the y-intercept works. And when we solve for y, we're going to find what the y value is when the x value is 0, which is our y-intercept. So we're going to write y equals 5 times 0 minus 6. Well, 5 times 0 is just 0, and we will be left with y equals 0 minus 6, which is just y equals negative 6. So our y-intercept is 0, comma, negative 6. Okay, so in this next question we're given the exact same instructions. Find the x and y-intercepts of the graph of the equation, but this time we're given a different equation. We're given y equals the square root of x plus 4, and I've put it in parentheses to show that x plus 4 is all under the square root sign, so it looks like that. So now that you saw how to do the last one, I want you to pause the video here and unpause it when you're finished, and we'll see how you did. So assuming you've solved it and you have your answer, let's work through it and see if you got it right. So once again, for the x-intercept, we know that just by the definition of what the x-intercept is, we can plug in 0 for y. So we have 0 equals x plus 4 squared. Now, in order to get rid of a square root, we have to raise it. We have to put the whole thing in parentheses and raise it by 2. We have to square it, essentially. We have to square both sides. So we'll do 0 squared, and then we'll raise this by 2. So 0 squared is just 0, and this root will cancel out, because basically what's going on is we're doing the root of x plus 4 times the root of x plus 4. And then so what we end up having is the root of x plus 4 squared, which just cancels out with that square root over there. So we're going to have 0 equals x plus 4, and then we're going to subtract 4 so that we can get x alone, and we have that our x-intercept is 0 minus 4, which is negative 4, comma 0. And again, if we want to check our answers, if we're even a little bit unsure, we can check our answers by plugging this into that equation and seeing if we get this y value out of it. So we do y equals the square root of negative 4 plus 4. Well, negative 4 plus 4 is just 0. So then we have the y equals the square root of 0, which is just 0. So y equals 0. And now we know for sure that this answer is correct. Now for the y-intercept, we're going to do a similar process, but once again, this time we're making the x 0. We're plugging in 0 for x instead of y, just because that's the definition of what the y-intercept is. So we have y equals the square root of 0 plus 4. Well, 0 plus 4 is just 4, so I'm kind of doing two steps here. 0 plus 4 is just 4, and the square root of 4 is just 2. So we have our y-intercept as being 0, comma 2. And once again, if you're unsure of your answer, just plug in 2 for y, or plug in 0 for x even. So we have y equals the square root of 0 plus 4. And then 0 plus 4 is just 4, and the square root of 4 is 2. So we plugged in the x value and got the y value out of it, so we know that this satisfies the equation and it is the y-intercept. Alright, so in this question we are given the exact same instructions, but a different equation. Our equation now is y equals the absolute value of 3x minus 7. So once again, I want you to pause the video here, try it for yourself, unpause it when you're done, and we'll see how you did. So assuming you've tried the problem, let's see how it's supposed to be worked out. So for the x-intercept, we already know that we're just going to plug in 0 for y. So we have 0 equals the absolute value of 3x minus 7. Well, in order to get x alone, which is what we have to do in order to get the x-intercept, we're going to add 7 to both sides. So we get 7 equals the absolute value of 3x. Now, to get x alone, we have to divide by 3. And so we have the absolute value of x, which we don't even need the absolute value anymore because it's just x in there. So we just have x equals 7/3. And then for our y-intercept, we are going to plug in 0 for x. Actually, this is supposed to be an ordered pair since it's an x-intercept, so it's 7/3 comma 0. For our y-intercept though, we're going to plug in 0 for x. So we have y equals the absolute value of 3 times 0 minus 7. So then we have the absolute value of 3 times 0, which is just 0, minus 7. 0 minus 7 is negative 7. So we have y equals the absolute value of negative 7. And the thing here to remember with the absolute value is that any number inside the absolute value becomes positive when it's evaluated. So the absolute value of negative 7 is just 7. So we have our y-intercept as being 0, 7. Okay, so for this next equation, same exact instructions, but a different equation. So our equation now is y equals 2x cubed minus 4x squared. Again, I want you to pause the video now, try it for yourself, unpause when you're done, and we'll see how you did. So assuming you've tried this for yourself, let's see how it should be worked out. So once again, for the x-intercept, we know that we're going to be plugging in y for 0 for y. So we have 0 equals 2x cubed minus 4x squared. Now here we're going to do a process called factoring, because in both of these terms, in 2x cubed and negative 4x squared, the thing they have in common is they both contain a 2 in them and an x squared. So that's actually what we're going to pull out. We're going to pull out 2x squared, and then in parentheses we're going to write x minus 2. So now this statement is the same exact thing as the statement above it, because if we distribute it, 2x squared times x is 2x cubed, and 2x squared times negative 2 is negative 4x squared. So now for this x-intercept, we have two separate things here. We have 2x squared equals 0, and x minus 2 equals 0. And if you think about it, that makes sense, because this is a cubic function, which looks something like that on the graph. So you can have 2 x-intercepts if you wanted. Even here we have 3. So 2x squared, for 2x squared equals 0, we're going to divide by 2. So 0 divided by 2 is 0. So we have x squared equals 0. And in order to get rid of the squared, we do the square root. So the square root of 0 is 0. So we're left with x equals 0, comma 0. That's one x-intercept, but that's not all of them. We have this one right here, x minus 2 equals 0. For this one, we just add 2, and we have x equals 2, comma 0. That's another x-intercept. For the y-intercept, we're going to do the same thing, or a similar thing, except once again we're just plugging in 0 wherever we see x. So y equals 2 times 0 cubed minus 4 times 0 squared. Well, 0 cubed is 0, because you're saying 0 times 0 times 0. So 0 cubed is 0, and 2 times 0 is 0. Now 0 squared is also 0, and 4 times 0 is 0. So ultimately what we're left with is 0 minus 0, which is just 0. Meaning that our x-intercept is going to be 0, comma 0. So for this next problem, we're given the exact same instructions, just a different equation. Y squared equals 6 minus x. So for the x-intercept, we're going to plug in 0 wherever we see y. So we have 0 squared equals 6 minus x. 0 squared is just going to be 0, leaving us with 6 minus x. So in order to get x alone, we have to subtract by 6 on both sides. So we have negative 6 equals negative x. And in order to get x alone, we have to divide by negative 1 on both sides, which gives us x equals 6, comma 0 as our x-intercept. And then for our y-intercept, we're going to plug in 0 wherever we see x. So we have y squared equals 6 minus 0, which is just 6. So then in order to get y alone, we have to take the square root of 6. So we have y equals, and here's the thing, when you take the square root of something, you have to write it as plus or minus the square root of 6, or whatever number you're taking the root of. And here's why. Let's say for an easier example, like if we had y squared equals 4, for example, when we take the root of that, we're asking what two numbers, when multiplied by themselves, give us 4. And that can either be 2 times 2, 2 positive 2's, or it can be 2 negative 2's, because a negative times a negative is still a positive. So when we do y squared equals 4, and we take the square root of 4, we have to write it as either plus or minus 2. That means 2 times 2 gives you 4, and negative 2 times negative 2 also gives you 4. So knowing that, we have to write plus or minus the square root of 6, and the square root of 6 isn't an even number, so I would just leave it as 0, comma, plus or minus the square root of 6. Okay, so for this next question, we are asked to use the algebraic tests to check for symmetry with respect to both axes and the origin. And the equation we're given is x squared minus y equals 0. Now, I want to go over the algebraic tests really quickly just to make sure we're on the same page. So, when it says check for symmetry with respect to both axes and the origin, It wants us to check for symmetry with the x-axis, symmetry about the y-axis, and symmetry about the origin algebraically. Well, what does that mean? Well, symmetry about the x-axis is a graph right here where if you were to take this part of the graph underneath the x-axis and flip it up, it would be the exact same as the piece of the graph above the x-axis. So basically, when we talk about graphs, we kind of stray away from y equals whatever and we move towards into f of x equals something. And f of x just means it's a function, and if you have an equation, then what you plug in for x is the x value, and the y value ends up being f of x. So you have an ordered pair that looks like x, comma f of x when working with a function. So in this case, if a graph is symmetric about the x-axis, that means that f of x it means that for every f of x point or for every y, there is a corresponding negative f of x, or that negative y value, the opposite of that y value. So if we want to check if the equation of the graph is symmetric about the x-axis, we replace y with a negative y and evaluate. And if we get that f of x out of negative f of x, then the equation of the graph is symmetric about the x-axis. So if you're ever trying to prove that the equation of the graph is symmetric about the x-axis, you always have to prove that f of x equals negative f of x. So in this equation I don't know if you're allowed to write f of x squared, so I just played it safe and I just wrote that the function f of x is y squared equals x. So now if we were to make a table here of values, and this is x and this is y, and we plug in, for example, 0 for x, then we have y squared equals 0, and then we would take the square root, and of course the square root of 0 is just 0, but it would technically be plus or minus 0, but that doesn't really matter. Now if we plug in another point for x, such as 4, and we plug that in, y squared, remember our y is our f of x, so this is x, and this is f of x. The function evaluated at x is what it means. So we have y squared equals 4. When we take the square root of 4, we know it can either be 2 times 2 or negative 2 times negative 2. So we have to write plus or minus 2. Now we can see here that for every x value, there is a positive y value and a negative y value, and it's always going to be the positive or negative of the same value. We're never going to plug in 4 for x and get negative 3 and positive 7 for y. We're always going to get the same number, just one is positive and one is negative. So that's symmetry about the x-axis. So if we're finding symmetry about the x-axis for this one, we plug in negative y for x, or for y, like that. So now we have x squared minus a negative y equals 0, and when we distribute this negative 1, this becomes positive y. So now we have x squared plus y equals 0, which is not the same equation. So f of x does not equal negative f of x. So this equation could not be symmetric about the x-axis. Now, symmetry with the y-axis is kind of the same thing, just on the y-axis here, and we'd be proving different things. But it's basically, if I take this piece of the graph, this section of the graph that's to the right of the y-axis, and I flip it over, it's the exact same as the piece of the graph that is on the left side of the y-axis. So for every corresponding f of x or y point on the graph, there is a corresponding x and a negative x on the graph which still satisfy the function. So here, if this is, for example, y equals 1, there's a positive x value here and there's a negative x value here, both of which will satisfy this equation. So that's why it would be symmetric. So in order to determine if a graph has symmetry about the y-axis, we have to replace x with negative x and evaluate the function. And if f of negative x equals f of x, then the equation is symmetric about the y-axis. So for this one, if we plug in, since f of x is the same thing as y, I'll just write it as y equals x squared for this purpose. So if we're looking to see if it's symmetric about the y-axis, we plug in negative x wherever we see x. And so we get y equals x squared, which is the same thing. So we have proven now that f of negative x, meaning the function evaluated at negative x, is the same thing as the function evaluated at x. And the reason for that is, if you have negative x times negative x, or if you have negative x squared, it's essentially just negative x times negative x, and a negative times a negative is a positive, and you just get x squared. So hopefully that helps a little bit, but the other type of symmetry is symmetry about the origin, which is a little bit more difficult, but still the same concept. It's basically, if you have a point here, x comma negative, or x comma f of x, then we have a corresponding point down here that is negative x, negative f of x. So that's what we have to prove when we're trying to prove if something has symmetry about the origin. So if we're trying to prove if something has symmetry about the origin, we plug in a negative x and a negative y and evaluate the equation, and if it's the same, then we know that it's symmetric about the origin. So for example, y equals x cubed. If we plug in negative y equals negative x cubed, we get negative y equals negative x cubed. That's just what it would be. And so then we would say that for every, I'm trying to explain this well, I don't know if I'm doing a good job though. For every point y and for every point x, there's a corresponding negative y and negative x. So I'll make another example here. For y equals x cubed, if we make a table here of x and y, and we plug in, let's say, 1 for x, then we get y equals 1 cubed, which is just 1, so y equals 1. Now if we have negative 1 for x, then negative 1 cubed is just negative 1, y equals negative 1. This differs from something like y equals x squared, because if we plug in negative 1 for x, then we would get y equals 1, because negative 1 squared is 1. So for every corresponding x and y, or for every x and y, there's an equivalent negative x and negative y. So back to the original problem here, if we're checking if it has symmetry about the y-axis, remember we have to plug in negative x wherever we see x. So we do negative x squared minus y, or negative x squared minus y equals 0. Negative x squared just evaluates to x squared, and then this minus y stays the same. Well, x squared minus y equals 0 is the same thing. It's the same equation as we were given. So we can say that f of negative x equals f of x, meaning that this equation is symmetric about the y-axis. So we know that it has y-axis symmetry. And I'll just abbreviate it to SYM. So if we're checking if it has origin symmetry, we plug in negative x wherever we see x and negative y wherever we see y. So negative x squared is x squared, and this negative 1 distributes and becomes positive y. So we can see that this is different. If it had origin symmetry, it would be the same thing. So this does not have origin symmetry. So therefore we can say that the equation of the graph only has y-axis symmetry. So in this next problem, we are once again asked to use the algebraic test to check for symmetry with respect to both axes and the origin. And the equation we're given is y equals x over x squared plus 1. So let's start with the y-axis, for example. Let's start with y-axis symmetry. If you remember, y-axis symmetry looks something like this, like a parabola. Meaning, if you plug in an x in the positive, if you plug in a positive x number and you plug in that same x number with a negative sign in front of it, you should get the same y value, which in other words means replace every x in the equation with a negative x, and if you get the same equation out of it, then it has y-axis symmetry. I hope I'm making more sense than I think I am, but basically it's like, you see how on this point, or you see on this example graph right here, we have this x value right here. Let's call that 2, for example. If this point here was 2, and then this point over here was negative 2. Well, both 2 and negative 2 have this same y value here. It has y-axis symmetry. It's symmetric with the y-axis. So if you took the equation of this graph and you replaced every x in that equation with a negative x and evaluated that equation, it would be the exact same as your original equation. And we can prove this because let's say we have the equation y equals x squared. Well, y equals x squared is a parabola like this. And for example, if we plug in 2 for x, we will get 4 right here for y. And if we plug in negative 2 for x, we still get negative 4 for y, or 4 for y. So we can see that on the graph it's symmetric with the y-axis, obviously, and then if we do the test, if we replace x with negative x and evaluate, well, we do negative x squared, which is just y equals x squared. It's the same, these two things are the same equation, meaning that it is symmetric with the y-axis. Now let's extrapolate that information and use that to solve this problem that we're currently on, x over x squared plus 1. So what we're going to want to do is replace every single x with a negative x. So negative x over, and if it's being squared, you want to put the negative sign in parentheses with the x to make sure that's all getting squared. So now we have y equals negative x over negative x squared plus 1. And if we evaluate, that negative x will stay the same. Negative x squared becomes x squared, and then we leave the plus 1. Well, the original equation is x over x squared plus 1, and this is negative x over x squared plus 1. So this does not have y-axis symmetry. Now let's go over to x-axis symmetry. Now if you recall, x-axis symmetry looks something like this. And just like how I was saying with y-axis symmetry, if we have this y value, let's call that y equals negative 2, and we have this y value, let's call that y equals 2. They both correspond to the same x value over here, meaning it's symmetric with the x-axis. Meaning, if we plug in a negative y, as in right here, to the equation and evaluate it, we should get the same equation out of it, just like with the parabola example. So the only difference between the parabola and this is that we're replacing y with negative y instead of x with negative x. So we have negative y equals x over x squared plus 1. In order to get rid of the negative 1 on the that's attached to the y, we just multiply both sides by negative 1. Negative 1 times the negative 1 in front of the y just gives us y. And we can think of this negative 1 as kind of negative 1 over 1. So this becomes negative x. And then because it's just a positive 1 down here, it's just x squared plus 1. Well, we can see, once again, x over x squared plus 1 is not the same as negative x over x squared plus 1. So we say that this does not have x-axis symmetry. So then we move on to origin symmetry. Origin symmetry is something like a cubic function, like this. This one's a little bit weirder to explain, but the general idea is that if you have this point, which is x comma y, and instead of using variables, let me pick random points. Let's say this is 2 comma 3. It means that you will have another point on the graph that's the exact same point as these, just the opposite sign. So you'll have negative 2 comma negative 3 down here. So in order to prove this, we have to replace every x and every y with their negative counterpart and evaluate the equation and see if we get an equivalent equation out of that. So we're going to replace all of our y's with negatives and all of our x's with negatives of that sign. So y becomes negative y, x becomes negative x. So we have negative y equals negative x over negative x squared plus 1. So for now we're just going to leave the negative y put. The negative x stays negative x. Negative x squared gets evaluated to x squared, and then we just put the plus 1 there. Now, to get rid of this negative sign in front of the y, we multiply by negative 1 on both sides. And once again, we can think of this as negative 1 over 1 if you want to, if that makes it easier for you. Negative 1 times the negative 1 in front of the y is just y. And negative x times negative 1, or I guess it would be negative 1 times the negative 1 in front of the x is x. And then x squared plus 1. That whole thing times 1. As we know, anything times 1 is itself. So we get x squared plus 1. So we're left with y equals x over x squared plus 1, which if we look at the original equation, we can see that the original equation and the one that we just evaluated are exactly the same, meaning this has origin symmetry. Okay, so in this next question we are asked to use the algebraic tests to check for symmetry with respect to both the x and the y-axis as well as the origin. And the equation we're given is x times y squared plus 10 equals 0. Now recall that to see if something has y-axis symmetry, we're basically looking to see if the graph will look something like this, basically. Meaning, if we plug in a x number and a negative x number, will we get the same y value? So in order to determine this, we just have to replace all the x's in the equation with a negative x and evaluate that equation and see if it's the same. So we have negative x times y squared plus 10 equals 0. And don't confuse this as negative x like negative x and a negative y or something like that. This is just negative x times a positive y squared. So in order to see if this is the same equation, we're going to subtract 10 on both sides. And so we'll have negative x times positive y squared equals negative 10. And then we divide by y squared. Because we're trying to get the x all alone, basically. So we have negative x equals negative 10 over y squared. And then we can multiply by negative 1 so that we can cancel out the negative 1 here and get x all on its own. And then so this is going to be multiplying by negative 1 over a positive 1, if that helps you to think about it that way. So then we're left with x equals 10 over y squared and now we're going to multiply both sides by y squared. Now we're moving everything back over to the x side to see if we get this equation right here when we're finished with it. So we're going to multiply everything by y squared, and I'm going to move this equation over here. So we have x times y squared equals 10. And so now we're going to subtract by 10 on both sides. And we are going to be left with our answer of x times y squared minus 10 equals 0. And if we look at our original equation, it's very close. It's just that in the original one we have plus 10, and in this one we have minus 10. So this equation does not have y-axis symmetry. The graph of this equation does not have y-axis symmetry. So then we move on to x-axis symmetry. Remember, with x-axis symmetry, we're going to be looking for a graph that looks something like this, meaning a y value here, and a y value here, I should say, and its equivalent negative y value here will give us the same x value here. Meaning that if we replace the y's in the equation with a negative y, if we replace the y's in the equation with the negative y and we get the same equation after evaluating, then it has x-axis symmetry. So we do x times negative y squared, all in parentheses, plus 10 equals 0. So x times negative, well, we're going to leave x there, we're just going to drop it down. Negative y squared is just y squared. And then we have positive 10 equals 0. Well, if we look at our original equation, x times y squared plus 10 equals 0. And we have x times y squared plus 10 equals 0 here. So we can say that the graph of this equation is symmetric about the x-axis. Now we do origin symmetry. And if you recall, origin symmetry looks something like this, like a cubic function, where if you have a point xy on here, you're going to have an equivalent point here that is negative x, negative y. So that means in order to prove that this the graph of this equation has origin symmetry, we have to replace all the x's and the y's in the equation with a negative x and a negative y, and then evaluate and see if it's the same equation as the original one. And if it is the same as the original one, then we know that it does have origin symmetry. So we're going to do negative x times negative y squared plus 10 equals 0. So we're just going to leave the negative x there for now, and then we're going to evaluate negative y squared as just y squared. So we have negative x times y squared plus 10 equals 0. Now, we could continue evaluating this like normal, or we could look at our y-axis symmetry work that we showed here, and we see that in y-axis symmetry we started out with negative x times y squared plus 10 equals 0, and that's the exact same thing we have here. And if we know that this doesn't have y-axis symmetry and it started out like this is the same equation, meaning it's just going to evaluate to x times y squared minus 10 equals 0, which is not the same as the original equation. So we can say that this does not have origin symmetry. It only has x-axis symmetry. Okay, so in the next question we are told to assume that the graph has the indicated type of symmetry, which we're told is y-axis, and then sketch the complete graph of the equation. So like we said, y-axis symmetry means that if we have a point x, like let's say this is x is negative 2 right here, that means there's going to be a point at that same value that's positive, I guess is how you would put it. So if we have negative 2 over here, we know there's going to be a positive 2. And all of that, and these 2 points are going to have the same y value, which is 0. So knowing that, we can know that this line right here is basically supposed to be reflected on this side here. So we know that it looks like this line kind of goes out of bounds on the y-axis right at the point negative 3, which means it's going to do the same thing at positive 3. So we can go ahead and draw it like that, and then we can kind of try our best to replicate this line here. And we can probably draw that a little bit better. Something like that. And that's just a rough sketch, which is what it wants us to do. It wants us to sketch the complete graph, but that's how you do that one. Alright, so in this next problem we are given the exact same instructions as the last one, but now we're told that this graph has origin symmetry, and this is the graph that we're given. So origin symmetry, if you recall, it means that if you have a point on the graph that's x comma y, for example, this point right here is 1 comma 0, it means you have another point on the graph that is the opposite of that x and the opposite of that y. So if this is 1, the opposite of 1 is negative 1. The opposite of 0 is just still 0, mathematically speaking, though. So we know that its origin symmetric point would be right here. Now, knowing that the origin symmetric point is always the opposite of the point that we're given in this case, we can see that, okay, let's take this point for example. I'm just going to assume that that's positive 1/2 and negative 1/4, like this. 1/2, negative 1/4. Its origin symmetric counterpart would be the opposite of this. It would be negative 1/2 and positive 1/4. Now knowing that, we can kind of see the pattern, and we can see that it would go down this way and kind of go out of bounds on the graph at the negative 2 point. So we can draw it like this, and we can say that that's our rough sketch of the graph, and that's how it would go. And once again, this is just a rough sketch. It doesn't have to be exact, but that's how you would do that one. Okay, so in this next question we're asked to identify any intercepts and test for symmetry, then sketch the graph of the equation. So this is really a multiple part question here. First we have to identify any intercepts, and then we have to test for symmetry, and then we have to sketch the graph of the equation. So let's break this down into our individual parts and solve it from there. So first let's start with the intercepts. If you don't recall what an intercept is, it's basically like let's say for the x-intercept for example. On the graph, the x-intercept is where the graph of the equation lies on the x-axis, meaning it's going to be some x value, comma 0, all the time for the x-intercept. For the y-intercept, it's where the graph of the equation crosses the y-axis. So it's the point that lies on the y-axis. So that's always going to be 0, comma some number y, which will change depending on which equation you're given. In this case, we're given the equation negative 3x plus 1. So if we want to find the x-intercept, we can plug in 0 for y, because we know that has to be the y value just by the definition of what an x-intercept is. So we start by plugging in 0 for y, so we have 0 equals negative 3x plus 1, and then we subtract 1, and we have negative 1 equals negative 3x, and we're trying to get x by itself here. So then we divide by negative 3, and a negative divided by a negative is a positive, so we get the x-intercept is 1/3, 0. Now then, we move on to the y-intercept, and we know that in the y-intercept the x value is always going to be 0, and the y value is going to change depending on which equation we're given. So we can plug in 0 for x to find the y-intercept. So we have y equals negative 3 times 0 plus 1. Negative 3 times 0 is just 0, and that 1 is the only remaining number. So we know that our y-intercept is 0, 1. Now we move on to testing for symmetry. So for origin symmetry, if you recall, it looks like a cubic function, like, let me draw that better. Like this, for example. It means if we have a point x comma y here, we also have the inverse negative x comma y also on the graph. So in order to test for origin symmetry, we have to replace x and y with negative x and negative y and evaluate the equation from there. And if it comes out to be the same, then we know it has origin symmetry. So we're going to do negative y equals negative 3 times negative x plus 1. So now we want to evaluate here. This negative y equals, so this is going to become a positive 3x, because essentially what we're doing is we're multiplying negative 3 by the negative 1 in front of the x and getting a 3x there. And then we're going to multiply by negative 1 on this side and on both sides, because that's how algebra works. So we have y equals, and then we have this negative 1 times 3x plus 1. So what we're going to do here is just distribute the negative 1 to both terms here. So we're going to end up with y equals negative 3x minus 1, which is not the original equation. So we can say this does not have origin symmetry. The next one, x-axis symmetry, looks like this. It means that for every point on the graph x here, or x comma y, there's another point on the graph called negative x comma y, which is, or x comma negative y, excuse me, which is just the inverse of the positive y value here, if that makes any sense. So what that means is that we have to replace y with negative y in the equation. So we have negative y equals negative 3x plus 1, and then we're going to multiply by negative 1 on both sides. So these two negative 1s are going to cancel out here, giving us y. Then we're going to distribute the negative 1 to both terms here, and that's going to give us y equals 3x minus 1, which we can see is not the same. So we can say that this does not have x-axis symmetry. Now we go to y-axis symmetry, which looks like this. So y-axis symmetry means that for any point on the graph x comma y, we also have a point on the graph negative x comma y. So in order to prove that an equation has y-axis symmetry, we have to replace x with negative x, and then evaluate the equation, and if it's the same, it has y-axis symmetry. So we have y equals negative 3 times negative x plus 1. and then negative 3 times negative x is just going to give us positive 3x. And we can see that that's not the same as the original equation, meaning that this does not have y-axis symmetry. So it doesn't have any symmetry as far as we can tell at this point. Now we have to sketch the graph. So we said that the x-intercept was at 1/3, 0. So we can put that down right here. And the y-intercept was at 1 or 0, 1, I believe. Yep. Now we can see that this is a linear equation. It's in mx plus b form, which is the standard form of a linear equation. So we know it's going to look like a line, and this negative 3 is the slope. So we know it's going to be fairly steep and negative in nature. So we can go, since the slope is negative 3, we can go up 3 on the y and over 1 on the x, because if you think about it, 3 over negative 1 is negative 3, and also the slope of a linear equation is rise, meaning the y value, over the run. So we have the rise of 3 over the run of negative 1. That being said, continuing on the right side of the graph, we go down another 3 and over another 1 to 1 1/3, which is right there. And if we're sketching a graph, this doesn't have to be super perfect, but we can say that the graph of the equation looks something like that. And that's how you would do that problem. And as you can see, this doesn't have y-axis symmetry, because if I have this point, or if I have this point right here, which is 4, negative 1. If this was symmetric with the y-axis, there would be a point that is, yeah, wait. No, I wrote that wrong. This is negative 1, 4. I switched around the points. Okay, so if this was symmetric with the y-axis, there would be a point at 1, 4, and as we can see, there is no point here at 1, 4. If this was symmetric with the x-axis, for example, this point, let's use the same thing, negative 1, 4. If this was symmetric with the x-axis, there would be a point at negative 1, negative 4. But as we can see, there isn't. If this was symmetric with the origin at negative, and we had the point negative 1, 4, if it was symmetric with the origin, there would also be a point at 1, negative 4. But we can see that there isn't. At 1, our point is negative 3. So we proved algebraically that it's not symmetric. It's not symmetric about the axis, both axes, or the origin. Nor is it, let me rephrase that. We proved algebraically that it's not symmetric about either of the axes or the origin, and we proved it graphically here. So that's how you do that one. Okay, so for this next problem, we're asked to identify any intercepts and test for symmetry, and then sketch the graph of the equation. And the equation we're given is y equals x squared minus 2x. So recall that the x-intercept is the point where the graph crosses the x-axis, meaning in order to find it, we just need to plug in 0 for y, because if it's crossing the x-axis at a point, our y value is going to be 0. So we do 0 equals x squared minus 2x. Now from here you might be wondering how you'd go about doing this, but if you look at both of these terms, x squared and negative 2x, you can see that the thing they both have in common is that they both contain an x, meaning we can pull out an x, we can factor out an x, and then that should allow us to continue the problem from there. So if we factor out an x, our equation is going to look like 0 equals x times x minus 2. And these two things are exactly equivalent, because if you distribute the x, you get x squared minus 2x, which is the exact same thing. Now we have two things happening here. We have x is equal to 0, meaning that one of our x-intercepts is 0, 0. And we have x minus 2 equals 0. So now we solve for x, meaning we add 2 to both sides, and we get x equals 2, which means that we have another x-intercept at 2, 0. And you might be wondering why you have two x-intercepts, and if you don't know why, it's because this is a parabola, meaning that it's going to look something like this in the end. Let me draw that better. It's going to look something like this in the end. If you don't know the parent graph of a parabola, that's fine. We're probably going to cover that in a later unit, but just know that if it has an x squared in it, it's going to look somewhat like a U-shape. If it's negative x squared, it's going to look like a lowercase n. But as we can see here, there are 2 points on the graph where the x-axis is being crossed, so it makes sense that we have two x-intercepts. So now to find the y-intercept, we do a similar process, except we're just going to plug in 0 for x, because the y-intercept is where the graph crosses the y-axis. So on a parabola like this, if it's crossing the y-axis, we know the x point has to be 0. So we plug in 0 for x, and we have y equals 0 squared minus 2 times 0. Well, 0 squared is 0, and negative 2 times 0 is 0, meaning our y-intercept is going to be at 0, 0. So that's our answer for this first part of the question, and now we move on to the part asking about symmetry. So, y-axis symmetry. If you recall, in order to test if something has y-axis symmetry, we have to plug in negative x wherever we see x and evaluate the equation, and if the equation is the same as the original equation, then it does have y-axis symmetry. So we're going to do y equals negative x squared, and the whole negative x is going to be in parentheses, minus 2 times negative x. Well, negative x squared is just x squared, and negative 2 times negative x is a positive 2x. So we look here and we see that this is x squared minus 2x, and we see here that we have x squared plus 2x. Well, those two equations are not the same, so this does not have y-axis symmetry. So then we move on to x-axis symmetry, and for that, remember, we're going to plug in negative y wherever we see y and evaluate the equation, and if it's the same as the original equation, then we've proven that it does have x-axis symmetry. So we're going to do negative y equals x squared minus 2x. Now we're going to multiply both sides by negative 1 to get rid of the negative 1 on the y. So we're left with y equals negative x squared plus 2x. And this is not the same as the original equation either, so we can say that this does not have x-axis symmetry. So then we move on to the origin symmetry, and to prove that something has origin symmetry, we need to plug in negative x wherever we see x and negative y wherever we see y and evaluate the equation. And if it's the same, then if it's the same as the original equation, then we've proven it has origin symmetry. So we're going to do negative y times negative x squared minus 2 times negative x. So we're going to leave this negative y here for just a moment, and we're going to evaluate negative x squared as x squared, and we're going to evaluate negative 2 times negative x as plus 2x. And now we're going to multiply both sides by negative 1. And we're going to get y equals negative x squared negative x squared minus 2x, which is close to our original equation, but in our original equation x squared is positive, and in this one it's negative. So we can say that this does not have origin symmetry. Now we move on to sketching the graph. Well, we know our x-intercepts are at 0, 0, and 2, 0, so let's plot those down. And our y-intercept is at 0, 0 as well. And we know that this is going to be an upward-facing parabola. And because we don't have much else to go off of there, I'm just going to make a table really quickly and plug in some values for x. So let's say 1, for example. If we plug in 1, so now we have y equals 1 squared minus 2 times 1. Well, 1 squared is 1, and negative 2 times 1 is negative 2, and 1 minus 2 is negative 1, meaning we have a point 1 comma negative 1 right here. So we know the graph is going to look something like that. And again, this doesn't have to be very exact because it just tells us to sketch it as long as we make it look like a parabola with these intercepts and with these x and y intercepts. Then we've basically done our job. And you might be saying, well, wait a minute, in previous examples, whenever you talk about y-axis symmetry, you always bring up a parabola and say that that has y-axis symmetry, so why doesn't this one? Well, in this example here, the parabola is centered at the origin, so if we were to flip one side of the parabola over onto the other, it would be exactly the same. But if we're flipping this onto the origin right here, if we're going directly on the y-axis, if we flip this side over here, it's not going to look the same. It's because this it's shifted, basically, is what I'm getting at. The parabola is shifted to the right a little bit. So because it's off of the origin, it's not symmetric with the y-axis. It is, however, symmetric with the point it is symmetric with the point 1 comma negative 1, because that's the vertex, but it is not symmetric with the y-axis. Alrighty, so in this next question we are asked to identify any intercepts and test for symmetry and then sketch the graph of the equation. And the equation we're given is y equals x cubed plus 3. So the procedure for finding the x-intercept is going to be same as before. We're just going to plug in 0 for y, and we have x cubed plus 3. And then we're going to subtract 3 to get x by itself. And we're going to have negative 3 equals x cubed. And in order to get rid of raising something to the third power, we need to take the cube root of it. So we're going to write the cube root here. And so we're going to have x equals the cubed root of negative 3. So our x-intercept is going to be the cube root of negative 3, comma 0. Now our y-intercept is going to be the same procedure as before. We're just going to plug in 0 for x. So we have y equals 0 cubed plus 3. And 0 cubed is 0, leaving us with just 3, meaning our y-intercept is 0, comma 3. Now for the symmetry test. So to test for y-axis symmetry, we're going to write y equals negative x, oh, I didn't even write the equal sign, y equals negative x cubed, and the negative is going in parentheses, plus 3. Well, negative x cubed is just negative x cubed. And if you're confused as to why, think about it like this. This cubed symbol is saying multiply it by itself 3 times. So we have negative x times negative x times negative x. Well, negative x times negative x is positive x, and then we drop this down here. So we have x times negative x equals negative x, or this would be x squared actually. So x times negative x is negative x cubed. So that's why. And then we can see that it's not the same as the original equation, so we can say that this does not have y-axis symmetry. So for x-axis symmetry, we're going to do something similar, except we're just going to plug in negative y wherever we see y. So we have negative y equals x cubed plus 3, and then we're going to multiply both sides by negative 1 to get rid of the negative 1 on the y side, and that's going to give us y equals negative x cubed minus 3. So we can see that that's not the same as the original equation either, so we can say that this does not have x-axis symmetry. And then for origin symmetry, we're going to do a mixture of the two. We're going to plug in negative y for y and negative x for x. So we have negative y equals negative x cubed plus 3. Well, we're going to leave this negative y here for just now. And negative x cubed, we've already said, is just negative x cubed plus 3. And then we're going to multiply both sides by 1. Or we're going to multiply both sides by negative 1. And so we get y equals x cubed minus 3. Which is it's not the same as the original equation. So this does not have origin symmetry. Now in order to sketch the graph, I'm going to take out my calculator here because I don't know what the cube root of negative 3 is. So the cube root of negative 3 is negative 1.44. So we go to negative 1.44, which is around here, comma 0, and we plot our point there, and we know that our y-intercept is 0, comma 3. So we go up here, and now we don't really have too much information to go off. We know that this is going to be some sort of cubic function, so it's going to look curved some sort of way. But I would suggest making a table here. And let's plug in 1, for example, for x. So we have y equals 1 cubed plus 3, which is 4. So we have our point 1, comma 4. So then let's do negative 1. And we have y equals negative 1 cubed plus 3. And negative 1 cubed is negative 1 plus 3, which is 2. So we have the point negative 1, comma 2. And then we can sketch the graph sort of like this. And that's how you would do that one. Okay, so in this question we are asked once again to identify any intercepts and test for symmetry, and then sketch the graph of the equation. And the equation we're given is y equals the square root of x minus 3. And I put that in parentheses so you would know that the square root is going over both the x and the minus 3. So it's like that. So let's start out by finding the intercepts, because that's just the first part of the question. So for the x-intercept, if you recall, in order to find that, we just plug in 0 for y and solve for x. So we're going to plug in 0 for y and write the square root of x minus 3. Well, in order to get rid of this square root symbol, because that's what's keeping us from getting x alone, because we can't add 3 to this side because of the square root being here. So we have to get rid of the square root somehow. And the way to do that is to undo the square root. And the way to undo the square root is to square it. So we're going to set this whole thing in parentheses and we're going to square it. And what we do to one side we must do to the other. So we're going to square this side as well. And 0 squared is 0. and we're left on this side with just x minus 3. So in order to get x alone, now all we have to do is add 3. And we get that our x-intercept is at 3, and then because we plugged in 0 for the y, we know that our y value is going to be 0. So that's our x-intercept. For our y-intercept, we're going to plug in 0 for x and solve for y. So we're going to do y equals the square root of 0 minus 3. Well, 0 minus 3 is just negative 3, so we're going to do the square root of negative 3. And we run into a problem. You can't take the square root of the negative number, because when you take the square root of something, you're essentially asking what number times what number, or what number times itself gives you the number under this radical here. And there's no number that you can multiply it by itself to get a negative number, if that makes any sense. So let's take the square root of 16, for example. We can do 4 times 4 to give us positive 16, or we can do negative 4 times negative 4, because you're taking one number and multiplying by itself. So we can't do 4 times negative 4, because those are two different numbers. Now, seeing that, you can see that there are no numbers that when you there are no real numbers that when you multiply it by itself, it will give you a negative number. And because we're working on the real number plane in this problem, in this chapter actually, because we're working in the real number plane, there are no real y-intercepts, so we can just write none. But more specifically, no real y-intercepts. If we were working in the imaginary plane, then we could probably come up with something. So those are intercepts. Now we move on to tests for symmetry. So for y-axis symmetry, we're going to replace the negative x we're going to replace the x in the equation with negative x and solve. So we're going to have y equals the square root of negative x minus 3. Well, if you look here, this is just blatantly not the same equation. There's nothing we can really do here. I mean, we could square this if you really wanted. If you really wanted to step through this and see that there is absolutely nothing you could do. So we have y squared equals negative x minus 3. But now we have to get y alone again. And in order to get y alone, we have to take the square root, and we're right back where we started. So there is no y-axis symmetry in the graph of this equation. For x-axis symmetry, we're going to replace y with negative y. So we're going to have negative y equals the square root of x minus 3. So we're going to multiply by negative 1 on both sides. And we're going to get y equals negative 1 times the quantity, or negative 1 times the square root of x minus 3. Well, this too isn't the same as the square root of x minus 3. So there's no x-axis symmetry either. Now we get to origin symmetry. So this is where we plug in negative x for x and negative y for y and solve. And if the equation comes out to be the same, then we know that it has origin symmetry. So we're going to write negative y equals the square root of negative x minus 3, and then we're going to multiply by negative 1 on both sides, and we're going to get y equals negative 1 times the square root of negative x minus 3. And we can see this is definitely not the original equation, so it does not have origin symmetry. So after doing all that, we know that the x-intercept is at 3, 0. So right there. We know that it has no y-intercepts. So this graph may go into this region over here, but I highly doubt it. I think we're mainly going to be looking over to this side over here. So let's make a table. And we're going to want to pick x values that are that are like greater than or equal to 3. Because let's say that we pick the point 1. Well, 1 minus 3 is negative 2, and you can't take the square root of negative 2. So let's start with 3, for example. Oh, well, that's going to be the x-intercept. Okay, so let's start with 4. So y equals the square root of 4 minus 3. That's going to give us 1, and that's going to give us the square root of 1, and the square root of 1 is just 1. So we have the point 4 comma 1. And then we can also do 7. So we have y equals, let me write this up here, y equals 7 minus 3. And 7 minus 3 is the square root of 4. And that's going to end up being 2. So at the point where x is 7, the y value is going to be 2. So we know this is 4, so we go 5, 6, 7, and we go up 2. And we know that this is not a linear equation, this is a square root function. So it's not going to look linear, it's going to look slightly curved. So we're just going to sketch the graph as looking like this. And that's just a basic rough sketch. We don't have to get it exactly perfect, but that is how you... Alright, so in this next question we are asked to identify any intercepts and test for symmetry, and then sketch the graph of the equation. So the equation we're given is y equals the absolute value of x minus 6. So let's start off by finding the x-intercepts, the x and y-intercepts. I'm just going to write this one as x-int, but this just means x-intercept. So recall that in order to find the x-intercept, you just plug in 0 for y, because we're finding the ordered pair on the graph where it's a number for x and then 0 for y. The value for x, though, will vary depending on the equation. So we're going to start off with 0 equals x minus 6, or 0 equals the absolute value of x minus 6. And to get x alone, we're just going to add by 6 on both sides. And we get the absolute value of x is equal to 6. And the absolute value of x is just x. So we get 6 equals x. So that means our ordered pair would be 6, 0. Now for our y-intercept, which I'm just going to write as y-int, we're going to plug in 0 for x, because the y-intercept is the ordered pair on the graph where it's 0 for x and a number for y, and that number will change depending on the different equations you're given. So we have y equals the absolute value of 0 minus 6. 0 minus 6 is negative 6. So we have y equals the absolute value of negative 6. And recall that when you're doing an absolute value, if the number is negative, it just becomes the positive version of that number. So we get y equals 6. Meaning that our ordered pair is going to be 0, 6. Now let's test for symmetry. Let's start off with y-axis symmetry. This is the symmetry, if you recall. This might just be something you have to memorize, or you can remember it just by knowing what it looks like on a graph. Remember, it looks like this parabola here. But this is the one where, this is the one where you plug in negative x for x and evaluate the equation, and if it's the same, then it's symmetric with y-axis. So we're going to start with y equals negative x minus 6 and in between the absolute value brackets. So we can't really evaluate this any further than what it already is, and we can just see that it's not the same equation. So this is not symmetric with the y-axis. Then when we move on to x-axis symmetry, which looks like this, remember, we're going to plug in negative y for y and solve the equation. So we have negative y equals the absolute value of x minus 6. Now we have to multiply by negative 1 on both sides to get the y alone. And this is going to be y equals negative, and then in parentheses, the absolute value of x minus 6. So this might look a little bit confusing, but you might be tempted to try to distribute these to the things inside the absolute value, but I would refrain from doing that, and I would just leave it like this, and then you see that it's not the same as the original equation, it's different. So we can say that this is not symmetric with the x-axis. So then we go to the origin symmetry, and this is the one where it looks like a cubic function like this, and this is the one where we plug in negative y for y and negative x for x and solve the equation to see if it's the same. So we're going to end up having negative y equals the absolute value of negative x minus 6. And in order to get this y by itself, we have to multiply both sides by negative 1. So we get y equals negative times, and then you want to put this in parentheses, the absolute value of negative x minus 6. And we can see once again that this is just not the same equation as here. So we can say this is not symmetric with the origin. So then we go to the graph here, and we know that our x-intercept is at 6, 0, so we count over 6 to right about here. And we know our y-intercept is 0, 6, which is off the graph, but I'm just going to estimate it as being somewhere over here. So now we have 2 points here, but it's still not enough to get a good idea of the shape of the graph here to sketch it. So let's plug in, for example, 1 for x. So we get y equals the absolute value of 1 minus 6, which is the absolute value of negative 5, and the absolute value of negative 5 is just 5. So we go to 1, 5, and then what's going to end up happening here, you can do this on the table, but I'm just going to explain it. What would end up happening here is that for each increase in the x-axis here, we would get a proportional decrease in the value of the y-axis. So at the point 2, 2 minus 6 is negative 4, and the absolute value of negative 4 is just positive 4. So we would continue going down this way, like that. Oh, I did that wrong, sorry. I got ahead of myself. 5 is actually up here, that was my mistake. So we would just continue going down this way. Until we get to x equals 5. 5 minus 6 is negative 1. The absolute value of negative 1 is 1. So we have our point 5, 1. And then we get here. And 6 minus 6 is 0. The absolute value of 0 would just be 0. So what happens after this? Well, let's plug in 7 for x. 7 minus 6 is 1. And the absolute value of a positive 1 is just 1. So now our point is 7, 1. And it would continue just the same. Now pat to the right of the x-intercept for every increase in the x-axis, there's a proportional increase in the y-axis. So we would go to 8, 2, and 9, 3, and then 10, 4. And our graph would look something like this. And then so now you're saying probably, well, why isn't this symmetric? If you flip this over on this side, wouldn't it be the same? And it would be, but it would be symmetric about the point 6, 0, not about the y-axis. So that's how you do that one. Okay, so in this next question, we are asked to identify any intercepts and test for symmetry, and then sketch the graph of the equation. And the equation we're given is x equals y squared minus 1. So in order to find the x-intercept, we're just going to plug in 0 for y and solve for x. So we have x equals 0 squared minus 1, and 0 squared is just 0, so we're left with x equals negative 1, meaning our x-intercept is negative 1, 0. So then for our y-intercept, we're going to plug in 0 for x and solve for y. So we're going to have 0 equals y squared minus 1, and we're going to add 1 to both sides, which leaves us with 1 equals y squared. And then we're going to take the square root in order to undo the squared. And the square root of 1 is just plus or minus 1. Meaning that our y-intercept is 0, plus or minus 1. So now we have to test for symmetry. So for y-axis symmetry, if you remember, we're going to plug in x with negative x and solve the equation, and if it's the same, then we know it's symmetric with the y-axis. So we have negative x equals y squared minus 1, right, yeah, minus 1. Then we're going to add 1 to both sides, and we have negative x plus 1 equals y squared. And then we're going to take the square root, and we're left with plus or minus the square root of negative x plus 1 equals y, which we can see is definitely not an equivalent equation. So we can say that this is not symmetric with the y-axis. Now for x-axis symmetry, we're going to plug in y with negative y and solve the equation. And if it's the same, then we know it's symmetric about the x-axis. The x-axis. So we're going to have we're going to have x equals negative y squared minus 1, and negative y squared is just y squared. So we have x equals y squared minus 1, which is the same equation. So we can say yes, this is symmetric about the x-axis. Now for origin symmetry, we're going to replace x with negative x and y with negative y and solve the equation, and if it's the same, then we know that it's symmetric about the origin. So we have negative x equals negative y squared plus or minus 1. So we're going to do 2 steps in one here. We're going to add 1 to both sides, and then we're going to square y. So we're going to have negative x plus 1, or we're going to square negative y. So negative y squared is just y squared. So now we have negative x plus 1 equals y squared. We're going to take the square root of both sides, and we're going to be left with plus or minus the square root of negative x plus 1 is equal to y, which is not the same equation. So we can say this is not symmetric about the origin. So then when we go to graph our points over here, we know that we have an x-intercept at negative 1, 0, and our y-intercept is at 0, plus or minus 1, meaning we have a y-intercept at 0, 1 and 0, negative 1. And then in order to get another set of points, let's make a table here. And let's say, well, what about when x is equal to 1? So we're going to have 1 equals y squared minus 1. And then that's going to give us, we have to add 1 to both sides. Actually, I don't like this way. Hold on. Let's plug in a point for y first and then solve for x, because when we plug in points for x, we might not get an even numbered answer or a whole number answer. We might get a root answer, which can be kind of difficult to graph. So let's see what our x value is when our y value is 2. So we have x equals 2 squared minus 1. And 2 squared is 4. And 4 minus 1 is 3. So when the x value is 3, our y value is 2. So we're going to graph it like this. And then because it's symmetric with the x-axis, we know there's an identical point over here. And then we just do a rough sketch of the graph, and it would look something like this. Okay, so in this next question we're asked to write the standard form of the equation of the circle with the given characteristics. And the characteristics we're given are that it has a center at 0, 0, the origin, and a radius of 4 units. So if you don't know the standard form of the equation of the circle, this is something you're going to want to memorize. And the standard form of the equation of the circle is x minus h squared plus y minus k squared equals r squared. And this h value is the x part of the center coordinates, if that makes any sense. So for example, in this center coordinates we're given, our x values, the x value here is 0, which means the h value here would be 0. Similarly, the k value is what this y value of the center is, so this would be 0 as well. And r is the radius. So we would write this as x minus 0 squared plus y minus 0 squared equals 4 squared. And this would just be x squared, this would just be y squared, and 4 squared is 16. So the equation of the circle is x squared plus y squared equals 16. Okay, so in this next question we're given the exact same question, but just different information. Our radius is still 4, but the center is still 2, negative 1. So now that you saw how to do the last one, I want you to try this one on your own, and then we'll come back to it and see how you did. So assuming that you've tried the problem, let's work through it and see how it would have been done. So if you remember the form of the equation, it's just x minus h squared plus y minus k squared equals r squared. So our h here is going to be this 2 here. So we're going to replace the h with the 2, and we get x minus 2 squared plus y minus, and then our k here is going to be negative 1. And so a negative minus a negative, meaning y minus a negative 1, is the same thing as a positive. So we can just write this as y plus 1 squared equals 4 squared. And if you didn't quite get this part, it's because this is essentially what I condensed. Y minus negative 1, because that's the y value. And then when you multiply this negative symbol, because it's technically a negative 1, by this negative 1, you get y plus 1. So that's why I did that. So we are left with x minus 2 squared plus y plus 1 squared equals 16. Okay, so in this next question we are asked to write the standard form of the equation of the circle with the given characteristics. And the characteristics we're given is that it has a center at -1, 2 and a solution point of 0, 0. So this actually differs from the previous two problems because in this one we're not given a radius, we're given a solution point. So what does that mean? Well, let's look at the graph over here. So our center is going to be at -1, 2. So we go to the left by 1 and up 2. And we have a solution point at 0, 0, meaning this is a point on the edge of the circle, if you want to call it that, meaning the circle will go kind of like this. That's a bad drawing, but that's just for example. The main takeaway here is that any point on the circle has to be equidistant to the center, meaning that if we draw a circle here, which is another bad example, but it's just like a thought experiment, I suppose, this point must be equidistant to the center, and this point must be equidistant to the center. These 2 points here have to be equal distance to the center in order for this to be even considered a circle. What that means, though, is that if I find the distance between the center and this solution point, then that can be used as a radius because all other points on the circle has to be the same distance away. So essentially the main takeaway is that you just have to find the radius using the distance formula, which if you don't remember, you should have it memorized by now. It's the square root of x squared, or x2 minus x1 squared plus y2 minus y1 squared. So we're going to do x2, which we'll say in this case is 0, minus x1, which is -1. So we have 0 minus a -1, and that's going to be squared, plus y squared, which is 0, minus 2, and that's going to be squared. 0 minus a -1 is the same thing as 0 plus 1, which is just 1. So we're left with 1 squared plus 0 minus 2 is -2 squared. So 1 squared is 1, and -2 squared is 4. So we're left with the square root of 1 plus 4, which is just the square root of 5. Meaning our radius is the square root of 5. So r equals the square root of 5 here. Now if we go to write the equation of the circle here, our h is going to be -1, so we're going to write x minus -1 squared plus y minus 2 squared, and we're going to be struggling for room here, equals, I'm going to draw an arrow here and just imagine this being there, root 5 squared. So x minus 1 is, or x minus -1 is just x plus 1, so we have x plus 1 squared plus y minus 2 squared, and the square root of 5 being squared cancels out the square root, so we're just left with 5, meaning the standard form of the equation of this circle is x plus 1 squared plus y minus 2 squared equals 5. Okay, so in this next question we're asked to write the standard form of the equation of the circle with the given characteristics. And the only characteristics we're given is that the endpoints of a diameter are 0, 0 and 6, 8. So you might be a little bit confused here. You might be saying, well, we weren't given the we weren't even given solution points, we weren't given a radius, we weren't given a center, so how could we ever find this out? Well, let's go to the graph here. So let me erase some of this. Okay, so one of the endpoints of the diameter is 0, 0, and the other one is 6, 8, which is going to be here and way off the graph, but we'll just put it right there. And a diameter, if you don't know, is a line segment connecting two kind of points on the circle. So this, for example, is a diameter, and then we can say that there's one half of the circle going here. That's a really bad drawing. Like one half of the circle going here, and then the other half is there. And of course this doesn't look like a perfect circle, but just imagine it being a perfect circle, I suppose. So in order to find the radius, for example, this distance here, half of the diameter is the radius. The radius is equal to the diameter divided by 2, or the diameter divided by 2. We're not given the actual length of the diameter, we're given two endpoints of the diameter though. But from these two endpoints, we can find the distance. And this distance right here is the diameter. And then we can divide that diameter by 2 in order to get the radius. So, we're going to do the distance formula first. So we're going to do x2 minus x1, so 6 minus 0 squared, plus y2 minus y1, so 8 minus 0 squared. 6 minus 0 squared, or 6 minus 0 is just 6, and that squared is 36. And 8 minus 0 is just 8, and 8 squared is 64. So we have the square root of 36 plus 64. 36 plus 64 is 100, and the square root of 100 is 10. So this is what we have so far. We have this line, this diameter here is equal to 10 units. So we know that the radius is essentially the midpoint, or if we have the center of the circle, let's just draw the center right here. The radius is half of the diameter. I hope that makes sense. I don't know if it does though, but just know that the radius is just half of this diameter. So half of 10 is 5. So the radius is equal to 5. Now we need to find the center to get our h and our k points. Well, how do we find the center? We know that if it's in between, if it's in the very middle of these 2 points, it's just the midpoint of those 2 points, right? So we just have to do the midpoint formula. So if you don't recall, you should have this memorized by now, but the midpoint is x1 plus x2 over 2, comma y1 plus y2 over 2. So our x1 is 6, and our x2 is 0, and that's going to be over 2. And our y1 is 8, and our y2 is 0, and that's going to be over 2. So 6 plus 0 is just 0, and 6 divided by 2 is 3, and 8 plus 0 is 8, and 8 divided by 2 is 4. So our center is at 3, 4. So now we have all the information we need to write this equation, write the standard form of the equation of the circle. So we're going to have x minus 3 squared plus y minus 4 squared equals 5 squared, which is 25. And that would be your final answer. Okay, so in this next question we're asked to find the center and the radius of the circle and sketch its graph. And the equation we're given is x squared plus y squared equals 25. So let's find the center first. Let's start with the center. So there's no number after the x or after the y that's in parentheses. For example, it doesn't say x minus 1 squared or y plus 3 squared, for example. And if you recall to previous problems, whenever the center was 0, 0, we always wrote it as x squared plus y squared. So we know our center, which I'm going to abbreviate as c, is just at 0, 0. And in order to find the radius, we're just going to take the square root of this number right here. So the square root of 25 is just 5. And you might be thinking to yourself, why don't you write it as plus or minus 5? Well, the reason it can only be a positive 5 is because the radius is a distance, and you cannot have a negative distance. So now let's sketch the graph. So our center is at 0, 0, and going directly upwards 5 units, we can get one endpoint of the circle, and going left 5 units, we can get another endpoint of the circle, because the radius is 5, so we're going 5 in every direction. Then we go 5 in this direction, and 5 in this direction. And now we have enough endpoints here to sketch the graph. So again, yeah, this is going to look pretty weird because there's more points on the x-axis than there are on the y-axis. So it's going to look pretty ovular, but hopefully on your graph it looks better than this. But yeah, that's a rough sketch. As long as you don't make it look like a diamond or a square or anything, you should be good. Okay, so in this next question, we're asked the same exact thing, but this time we're given a different equation. We're given x minus 1 squared plus y plus 3 squared equals 9. So now that you saw how to do the last one, I want you to try this one on your own, and then we're going to come back to it and see if you got it. So assuming that you've tried this problem on your own, let's see how it would be done. So let's start with the center. So the center I'm actually just going to write and then explain in a little bit. It would be 1 comma negative 3. And the reason it's not negative 1 comma 3 is because in the equation of the circle it's x minus h. Meaning that if I wrote the center as negative 1 comma positive 3, then when I did this x part, I would get x minus a negative 1, which is x plus 1, which is not correct. So instead we write it as the opposite of what you see in here. And then in order to do the radius, we just take the square root of 9, which is 3. And it's as easy as that. And then we go to graph the equation, which has a center at 1 comma negative 3 and a radius of 3 points, or 3 units. So we go up, or we go 3 in every direction. 1, 2, 3. 1, 2, 3. And this part is going to be off the graph. And we can form a rough idea of what this circle looks like. So in this next question, we are given the exact same question, just a different equation. And our new equation is x minus 1/2 squared plus y minus 1/2 squared equals 9/4. So once again, let's start with the center. And just like before, we're just going to write the numbers we see in here, just the opposite sign. So how this says negative 1/2, we're just going to write 1/2. And how this says negative 1/2, we're just going to write 1/2. And we get that our center is at 1/2 comma 1/2. Now in order to do the radius, we're going to do the square root of 9 over 4. Now recall that it's a property of square roots that if you're taking the square root of a fraction, then you square root both the numerator and the denominator, meaning we're going to have the square root of 9 over the square root of 4, which comes out to be 3 over 2, which is just 1 and 1/2. So when we go to graph it, our center is at 1/2, comma 1/2. And then we're going to go 1 and 1/2 units in every direction in order to get the endpoints. So we go 1 and 1/2, then we go 1 and 1/2, then we go 1 and 1/2, and finally 1 and 1/2. And from there we can sketch the graph of this circle. And that's a really bad sketch, so I'm going to do that again.